So I just held a heavy book against the wall, and we asked, do you have to push up to hold it in place? You said no. Well, how is that possible? Here's the book. What are the forces acting on it? Get the obvious one. Okay. Was it accelerating down? Was it accelerating up? So I know there has to be an arrow same size pointing up. Not quite sure what that is yet. I think I know, but let's just file that I have to fill that one in and identify it. I know it's there. What else? Well, let's pretend the wall is right here. So let's pretend that I applied a force on the book. I pushed on the book that way with F applied. Forces come in. If I push on the book, there's also, and the book pushes against the wall, there's also a normal force pushing out. That should be the same size as F applied. I don't think I eyeballed that very good, Raphael. Let me try that again. About there, I think. A little closer. Anybody want to guess what that upwards force is? Yeah, it's friction. What if the wall was made of ice? Would I have to push harder, or could I ease up? Pardon me? Harder. What if the wall was covered in sandpaper? Would I have to push harder, or could I push less? Push less. Okay. Is that all right? So it's kind of a neat little free body diagram. I'm not going to throw it at you on a test or anything, physics 12 maybe, but just kind of let you know, yeah, it is very possible. But that's not the point of today's lesson. The point of today's lesson, we're going to be doing what we call many body problems. Problems where there's more than one mass connected by strings. So in these problems, we have several objects connected by strings, but we're going to add a limitation. If they're connected by strings, Kevin, we can only accelerate, Tyson, look up, we can only accelerate smoothly. We're not allowed to do this. That's actually in physics called a jerk. It's a physics concept, and the physics of a jerk is really, really tricky. Here's my point. Kevin, I'm going to argue that if the mass in my left hand on your right is accelerating forward at 2 meters per second squared, this hanging mass is accelerating upwards at 2 meters per second squared. I'm going to argue that it's impossible for these to be accelerating at different rates. Different directions, yes, but as long as it's a smooth pull, the magnitude of their acceleration is going to be the same. Yeah? What does that mean? So I wrote down here, the easy approach is to realize because they're accelerating at the same rate, we can treat the system as a single object. We can treat them as one big mass. Example 1, I like example 1, I like example 1. I like. Actually, is there friction in example 1? No? Too easy. Once there's friction, then I like example 1, example 1, example 1. What does it want me to find, Victor? And you know what this is a good job for? Did they give me a picture? I'm going to label the picture. Okay, do you see the chain of events I went there? Now, why did I know that I did? First, it doesn't say net force, so I can't go straight to F equals ma. Let's do a free body diagram. So on the left here, on this 3 kilogram mass, Victor, what are the forces acting on it? Get the obvious one. Is there more than one mass in this question? Is there more than one mass in this picture? I'm going to call it M1G. You know what I'm going to call the other mass? Can you guess? M5? 2! That's a way better idea. Yeah, let's go with M2. Okay. Is it sinking into the ground like quicksand? Flying here like Superman? So, and you know what? I'm going to call it normal force number 1 to go with mass number, wait for it, 1. Is that all right? What else? Is this 20 touching the 3? Is this 20 touching the 3? So don't tell me 20. What else? You know what's right here? A rope. Who remembers, what do you call the force from a rope? Tension. You're feeling it right now? Tension. Those are the 3 forces acting on mass 1. What's causing mass 1 to accelerate is this rope, tension. What's causing everything to accelerate? Well, mass 2 is getting pulled by this, and some of that. Let's go through it. Let's keep going. Quinn, what are the forces acting on mass 2? Get the obvious one. I'm going to call it M2G. The mass changes, not gravity. Normal force number 2 to go with mass number 2. Now, you don't have to call this one 2. You could have called this one 1 and this one 2. I will always label my diagrams from left to right. So if you want your work to look like my answer key, start on the left and work your way across. So the one on the far left is mass 1, the next one is mass 2, the next one is mass 3. You don't have to, no rule. But if you're wanting your to look like mine, that's how I'll do it. What else? We have this 20 coming from off the page. What do we call the mystery force coming from off the page? You remember? Yep. There's definitely an F applied. We're missing one more. Can we see it? Mu equals 0. I think we're on a frictionless surface. But we're missing one more. And the one that we're missing is because forces come in. What are we missing? Tension is slowing the 2 down as it's speeding the 3 up. There's always tension on both ends of a rope if they're connected to things. There's our equation. Victor, what did part A want me to find? I'm going to, listen close, find the acceleration of everything by writing an equation for everything. Paige, what does part B want me to find? You're feeling it right now? Tension? Listen close, Paige. I'm going to find an individual force by writing an equation for an individual mass. So you want me to find the acceleration of everything? I'll write an equation for everything. What I'm going to do is I'm going to walk along the rope like that. Which way do you think this is accelerating? Which direction is the, he said to the right, he's correct. Which direction is the winning direction? Same answer. So I'm going to walk along the rope. Anything pointing to the right is going to be winner plus. Anything pointing to the left is going to be loser minus. You okay with that? I'm not going to include any vertical forces because I'm walking along the rope here. So what's my equation going to look like? Winner, F applied. Let's write that down here where we have some space. And then as I walk along the rope, I run into this first tension. What's this first tension, winner or loser? Loser minus. Then I run into this next tension. Winner plus. Have I reached the end of the rope? Yes. Equals. What does winner minus loser equal? Here's the tweak. Odetta, do you notice we have forces from more than one mass on the left? We have to have more than one mass on the right. M all times A. What do I mean by M all? M1 plus M2. All the masses times A. Everybody put your pencils down. Everybody stretch. Cheers. You know why we're stretching? These equations are great. Every time you do them, you lose a little tension, which is always nice. Oh, that's like so relaxing. That's not my best worst joke. It's coming yet. But if you set these up right, when you write your equation for everything, the tensions will cancel. And if you want to, every time you do that, put your pencil down and stretch it out. Feel free. It's just kind of giggly silly, but also just kind of nice. Ooh, back to you, Victor. What were they asking me to find? How would I get the A by itself? Which one of those answers is correct? Multiply by M all or divide by M all? Divide. So you're telling me that A is going to be F applied divided by M all? Say yes. What was F applied? And M all, that's going to be 3 plus 2. I'll bet, Victor, you might even be able to do that in your head. It's 20 divided by 5. Can you get that answer in your head so that the YouTube people think you're oh so clever? Very nice. I'll even go to 2 sig figs, 4.0 meters per second squared. How do we handle more than one mass? We kind of get clever and say, well, let's pretend it's just one big mass. One big Ubermass. And it's winner minus loser equals M all A, which I guess you've always technically been doing, because when it was one mass was M all. It's always been winner minus loser equals M all A. We just never had to emphasize that before. Tyson, what did B want me to find? I'm going to write an individual mass equation for an individual force. I'm going to write an equation for mass 1. I'm going to quickly, in fact, all of us, let's quickly redo the free body diagram down here. It was M1G, normal force 1, tension. I don't care about mass 2. I'm pretending mass 2 does not exist. Tyson, which way is that 3 accelerating? To the? Which way is the winning direction? Same answer. To the? So everybody, who's winning? Look at your free body diagram here. Who's winning? Tension. Who's losing? It's a trick question. Maxine, I don't know what this means. What does this mean? No loser. What does winner minus loser always equal, Tyson? Yep. Now, are we looking at both masses this time? So no. Which mass? Mass number? M1A. To find an individual force, I go write an equation for an individual mass. Hey, Tyson, what was M1? From the picture. Yep. Hey, Tyson, what was the acceleration? We just figured that out. Tyson, I'll bet you can even do that in your head. What's the tension in newtons? Look at you doing clever math in your head. Mr. Dewick, what if instead of mass 1, what if I'd written an equation for mass 2? You know, it'd be really cool. It would be really cool if when we wrote an equation for mass 2 and solved for tension, we also got 12. It would be really neat if it didn't matter which mass you picked, pick the easiest one. Luis, that would be cool. Hey, you know what? Let's write a free body diagram, Luis, for mass 2. I think we had M2G, yes? We had normal force 2. We had F applied. And we had tension pointing left. Luis, which way is mass 2 by the way, and again, I'm just going to ignore that one because I'm finding an individual force. I'll look at an individual mass. Which way is mass 2 accelerating? To the? Which way is the winning direction? Same answer. Who's winning? Who's losing? Equals? Which M? M2. So we get this. F applied minus tension equals M2A. What am I trying to find? Tension. Luis, what's right in front of the T that I don't like? Swappy dance time. I'm going to plus the tension there. I'm going to minus the M2A there. When I do that, I'll get F applied minus M2A equals tension. But Luis, do you mind? I'm going to put the T equals on this side because that's where we're used to seeing it. Luis, how big was the applied force? Yep. How big is M2? What was the acceleration? It would be neat if that also worked out to 12. That'd be really cool. Does it? So what you're going to have in your many body problems often is I'll ask you to find the acceleration and then I'll ask you to find the tension. You write an equation for everything to find the acceleration for everything. Why can't I use this equation for everything to find tension? Why doesn't this work? The tensions cancel out. That's a problem. We'd like to find tension, but we have a bit of a tension, we have a deficit of tensions. One could say that this equation has a tension deficit disorder. Booyah! Isn't that a terrible joke? It's missing the tensions. It has a deficit of tensions. It has a tension deficit disorder. Oh, someone just got it there. Okay, sorry. Should have slowed it down for Mesa. Attention deficit disorder. Nothing. Wow. Okay. We're going to pick up with this next class because I'm missing a few humans, and also I want to get to the Mythbusters video. So let me hit pause for a second.